Hello students and welcome back to study room. So as I told you that now we are going to do electromagnetic induction. Now what is electromagnetic induction? First I just want to explain the meaning of these two words to you. So we know electro means relating to electricity. Magnetic obviously means relating to magnetism. And induction or the word induce. Induction comes from the base word induce, right? So this word induce actually means giving rise to or producing. This is the meaning of induce. Like inducing something means that you are making something happen from outside, that something that is naturally not happening. Okay, so you will see what this actually means. So in this chapter, what did we do? We saw that a current carrying wire produces a magnetic field. That's what we saw in case of a straight wire, in case of a loop, a wound wire which is called a solenoid. So we saw all of these produce magnetic field because current produces magnetic field. Now in electromagnetic induction, we are going to study the opposite thing. We are going to see that can a magnetic field in some way produce a current also. Okay, we are actually trying to do the opposite to what we had earlier studied. Like a current produces a magnetic field. Now we're going to study can a magnetic field in any way produce a current. Now, how have you seen any current flowing in a wire? Whenever you say that a current I is flowing through this wire, when does it flow? It flows when that wire is a part of a circuit which has a battery, right? Because we studied this in current electricity that current only flows, even if it's air current or water current, only flows where there is some difference, right? So in case of current electricity, that difference is a potential difference, right? So current will only flow when there is a potential difference across the wires, which earlier we saw was maintained by a battery or a collection of cells, right? So in electromagnetic induction, what we're going to try to see is that can we make current flow in this conductor or in any wire without there being a battery connected? That means if the battery is not there for providing a potential difference, then there has to be something else. Okay, so keeping this in mind, we'll move forward. Okay, let's go. Okay, so first we're going to study about this So first we're going to study about this instrument called a galvanometer. So if you remember, we studied what is an ammeter. An ammeter is an instrument that measured how much current is flowing through a wire or a circuit, right? Or any resistor. A voltmeter is what measures a voltage difference or a potential difference across 2 points. Now we have a new instrument which is called the galvanometer. Let's see what the galvanometer does. So it's written here that a galvanometer is an instrument that can detect. This is the important word in case of a galvanometer. It doesn't measure anything. Like if a voltmeter is connected across a resistor, it would give you the potential difference with a unit in volts. It is going to tell you 5 volts potential difference across this wire or a resistor. If an ammeter is connected, it will tell you 3 amperes of current is flowing or 4 amperes of current is flowing. But the galvanometer doesn't actually give you any measure of the current or whatever it measures. It only tells you if a current is there or not. It only detects the current in a circuit. So see, it only detects the presence of a current in a circuit. Okay, it can deflect either to the left side or of the zero mark or the right side depending on the direction of current. So basically, if I have to represent it for you, if this is the face of your galvanometer and this is its pointer. It has a pointer and this is the zero of the galvanometer. So at the zero position, the pointer remains exactly in the middle. Okay, you can also look at this diagram that is shown to you. I'll explain it to you with my diagram first and then I'll come to this diagram. Okay, so we know now that the zero of the galvanometer is exactly in the middle, and then here there is the 1, 2, 3 and so on. Here also there is 1, 2 and 3. So this 1, 2, 3 don't show you the amperes current. It doesn't show you this. 1 doesn't mean 1 ampere, 2 ampere, 3 ampere. No, this only means the strength of the current. So say the galvanometer is connected in a circuit which has some current in it. The galvanometer is represented by a capital G. Okay, so if it is connected in a circuit with a battery, obviously current will flow through it. So what will happen is, this galvanometer, this is the zero of the galvanometer, the needle will deflect towards one side. Either it will deflect towards the left side or it will deflect towards the right hand side, depending on the direction of current. So what is the two things the galvanometer shows you? The presence and direction of current. Okay, so these are the two things that a galvanometer will tell you, if there is a current in the circuit or not, and it will also tell you the direction the current is in. What do I mean by that? Say if you connect a galvanometer in this circuit, okay, this is your galvanometer, and here you have a battery and a key. If you close this key, that means there is a current flowing in this direction, right? Now in this case, if the galvanometer, I'm not saying when the current is flowing towards the right, the galvanometer needle will always go towards the right. It depends on the calibration of the galvanometer also. Okay, it does not necessarily mean if the current is flowing towards the right, the deflection is towards the right, but it shows you a relative deflection. How? I'll tell you. Look, this current I is flowing in this circuit in the rightward direction here. So say in this case galvanometer deflects towards the left. Say this is an example. Then what happens is, if we take the same galvanometer, we take the same battery and we connect the battery opposite. That means this time here it was positive negative, now it's negative positive, and now the current obviously flows in this direction. So now the galvanometer will deflect towards the right. So this is just going to tell you that the direction of current has been reversed. Okay, so these are the things that you need to know. If there is no current in the circuit, the galvanometer would remain, the needle would remain exactly at the zero position, straight like this. If there is a current, it will deflect either to the left or to the right. If the current is stronger, it will deflect more to the left or the right. Okay, less current, less deflection, more current, more deflection. Okay, now keeping this in mind, we'll move forward. So now we're going to study the Faraday's experiment. So Michael Faraday was an experimental physicist, and what was the experiment he conducted? So the experiment he conducted was this. What he did was, he moved a magnet inside a coil connected to a galvanometer across the coil. Let me read it, then I'll explain it. Okay, when the magnet is at rest, there is no deflection in the galvanometer. Okay, now what does that mean? That means we take one coil, which means we take a wire, and we just coil it like this, kind of in the shape of a solenoid, right? But you remember, solenoid was obviously connected across a battery because it had to have some current, due to which there was a rise to a magnetic field, which gave rise to a magnetic field. That's what we studied. But here we don't have any current in this coil. We are only connecting it across a galvanometer. Why are we connecting it across a galvanometer? Because we want to see if whatever experiment we are doing, because of that there is any current generated in the wire. You remember when we were starting this topic, I said that we want to see if the magnetic field in any way can give rise to a current in the coil without a battery being attached to a coil. So this is what I meant by it. So here we have this galvanometer attached to a coil. This coil actually could be wound around a cylinder also. Anyway, if you want to keep the coil like this, you can keep it like this also. Okay, now what we are doing is, we are taking this magnet. Right now we are taking this north pole here and the south pole here. What we are doing is, we take this magnet close to the coil. We take it near the coil. So what do we see? We see that as soon as we move the magnet towards the coil, there is a deflection in the galvanometer. Okay, say in this figure also it shows that, can you see this small arrow here inside the galvanometer? Like this is the galvanometer, this is the scale of the galvanometer, and you can see this small arrow here. Can you see that? That means that the galvanometer deflects towards the right. Okay, great. So what happened? When the magnet is at rest, when the magnet is not moving, there is no deflection. So what does that mean? That means, what does that mean? That means that when the magnet is at rest, no current in coil. Obviously, right? Because it is given to us and it was observed in the experiment that when the magnet is just kept, this is the coil, this is the magnet. When they're just kept like this, no deflection in the galvanometer. That means no current in the coil. Great. Now what we did was, let's go forward. We did this. When the magnet is moved towards the coil, the needle of the galvanometer deflects in one direction. Now here in this, it is showing that when the magnet is moved like this, which means when the north pole is moved towards the coil, there is a deflection towards the right. Right? So now we can write that when north of magnet is moved towards coil, deflection towards right is produced. Right? We can see this in the figure. I'm saying it according to the figure. I'm not making this up. Okay. Then what we saw was, when this first thing we did, we kept the magnet and coil stationary away from each other, no deflection, so no current. When we took it close, we saw as soon as we moved the magnet closer, there is a deflection towards the right. When we took the north pole closer, there is a deflection towards the right. But when we take it closer and stop it there is just one quick deflection and the galvanometer needle comes to zero again. What does that mean? That deflection toward the right was only because of the movement of the bar magnet. As soon as the bar magnet is moved and kept close and stationary, it is not moved again, there is no deflection. That means that the current was only momentarily produced, or only produced for a split second when the magnet was in motion. It's not like as soon as the magnet is brought close, the galvanometer is continuously showing it towards the right. No, that is not what's happening. There is only a momentary deflection of the galvanometer. Okay. What does that mean? That means that the current is only produced when the magnet is in motion. Okay. So I'm writing current is only produced when magnet is in motion. And why did I say that? I said that because when we wrote this, the first point, when the north pole of the magnet is moved towards the coil, there is a momentary. I'm going to write momentary here. This is an important word because momentary means that it was just for a split second and it came back to zero. It wasn't a deflection like when you moved it towards the coil, the galvanometer went to the right and it stayed there. If it stayed there, that means there was a continuous current that was being generated. But if it just went towards the right once and it came back, what does that mean? That the current was just generated and it went away as soon as the magnet stopped moving. Okay. So when the magnet is near coil but not moving, galvanometer shows, I'm writing galvanometer G, shows no deflection. Okay. We know this now. Then what do we do? The next thing, come here to your PPT. When the magnet is moved away from the coil, the deflection in the needle is in the opposite direction. Again, momentary deflection. What happens? When north of magnet, why am I saying north of magnet? Because the north pole is is towards the coil. That's why I'm saying when the north pole is moved away from the magnet or coil or towards the coil. That's why I'm saying the north pole, because I'm trying to specify it according to the figure that is given. Okay. When north of magnet is moved away, again, momentary deflection. Deflection. And galvanometer shows 0 as soon as bar magnet stops moving. Okay, this much is clear to you. This is just the experiment. I'm just telling you what was observed. Then, what was the conclusion? This is the conclusion that Faraday brought. Faraday concluded that whenever there is relative motion between a conductor. Now it would make sense to you why I was again and again writing that as soon as the magnet is at rest, no deflection in galvanometer, and the deflection only is momentary when the bar magnet is moving. What does that mean? That the current is only produced when there is a relative motion between the bar magnet and the coil. What does relative motion mean? This means that no matter which one is moving, if the coil is moving, then only the same thing happens. If the bar magnet is moving, then also the same thing happens. So it is a relative motion. It's not just that the coil has to be fixed and only the magnet can be moved. The magnet could also be fixed and the coil will be moved, and the same thing will be observed, that momentary deflection when the coil is moved towards it, and the galvanometer shows 0 as soon as the coil stops. Then when you take it away, a momentary deflection toward the opposite direction, which stops once the coil is at rest. Okay, so we see that induced potential difference is produced when there is this relative motion between the magnet and the coil. Okay, so this is what is important for you, which produces an electric current which is induced. Okay, so if I have to sum it up for you, you will say that relative motion between coil and magnet produces current. That is why am I saying relative motion? Because we saw that as soon as the bar magnet was brought close and it was kept there, the deflection is 0. That means only if we keep the bar magnet moving with respect to the coil, if we keep getting it closer or farther, only then the current will be continuously generated. That means if either coil or magnet is at rest, no current will be produced. Okay? You can also do this activity with the north pole facing otherwise. Like you can do this like this. If the bar magnet is kept like this, south here and north here, you will observe the same thing but in the opposite way. Do you remember what had happened when we took the north of the bar magnet close? There was a deflection toward the right first. Now this time when you take the south close, there would be a deflection toward the left first. Okay, and then when you take it away, there would be a deflection towards the right. Okay, so all you have to remember is no matter which pole you are bringing, when it is quickly moved towards the coil, there is a deflection towards one direction, and when you quickly move it away, the deflection is in the other direction, and when you keep it stationary with respect to the coil, there is no deflection in the galvanometer, which means there is no current. So this process of inducing a current. Now we come back to the word induce that I told you. Here we are inducing a current because is there a battery connected to the coil? Is there a potential difference generated by the battery? No, the potential difference is not generated by the battery. The potential difference is generated because of the relative movement between the coil and the battery. So what does that mean? That means that there is an induced potential difference. That means it's not actually there. We are doing something from outside to generate a potential difference, and there is no current actually there. There is no actual current in the coil originally, right? There is no battery, so there is no current, but we are inducing a current because of the movement of the battery with respect to the movement of the bar magnet with respect to the coil. So we say that current is induced in the coil due to the relative motion between coil and magnet. Okay, and current is induced because before that a potential difference is induced. Obviously current will only flow when there is a potential difference, right? So potential difference is induced, and because of that a induced current flows. Okay, I hope this is clear to you.